is Salcedo, the leader of Euclidean algorithm, and I want to introduce to you the discussion of our tribe for our topics. Our topics are the chapter 11, the mathematics of graphs, and also the chapter 12, the modular arithmetic. Now, let's start the discussion. I hope you jot down the important information. And I have these 3 reminders. First, watch. Second, learn. And third, understand the information.
Hi everyone, my name is RGB Tomenyo from Tribe 5. Our lesson for today is about graphs and Euler circuits. Graph theory, Euler paths, and Euler circuits. An Euler path is a path that uses every edge in a graph. With no repeats, being a path, it does not have to return on the starting vertex. An Euler circuit is a circuit that uses every edge in a graph with no repeats. Being a circuit, it must start at the end at the same vertex. So in the first example, makita natin yung arrow. Nagsimula siya sa C, pupunta sa B, pupunta sa A, pupunta sa C, and pupunta sa D. In the next example, makita natin yung circle. Nagsimula siya sa B. Ay, sa A. Nagsimula siya sa A to B, go to B, to C, and to C, to A to D, from D to C. All of the edges are exactly 1. So, the next example is the Euler circuits. Makita natin yung parang pencil, makita natin yung arrow kung pupunta saan. So nag-start siya sa letter B. We start at letter B, from B to A to A to E, back to B, back to C, to D, to E, and back to B. So yan po. The difference of the two is the path is now returning to starting vertex, while the Euler circuits must start and end at the same vertex. Euler path and Euler theorems. Graph will contain an Euler path if it contains at the most 2 vertices of a degree. A graph will contain Euler circuits if all vertices have a degree, even degree. So makita natin yung degree to 0, degree to larger. So makita natin sa example, sa una, the graph does have an Euler path. So makita natin kung magsimula tayo sa B, magkakaroon ng problema dahil ma-miss natin yung letter F papunta sa B. So in the second example, makita natin dito yung picture sa baba, magsisimula tayo sa letter C. So, simula sa C, papunta sa D, to E, E to F, F to C, C to B, B to A, and A to F. Euler path, C, D, E, F, C, B, A, F. A graph will contain an Euler path. It contains at the most 2 vertices of a degree. So, makita natin na dapat yung number is a degree. So, the graph does have an Euler path. The graph does not have an Euler path. Makita natin sa pangalawa, drawing, dahil sa tatlong tree, siya ay even degree. In the next, the graph does have an Euler circuit. A graph will contain an Euler circuit if all vertices have even degree. Hanapin naman natin dito yung even degree. So ayan, makita natin, the graph does have an Euler circuit. Euler circuit C, B, A, F, C, D, E, F, and C. The numbering is the edges. So, ayan na po. So, ito naman is an Euler circuit. The graph does have an Euler circuit. And the next example, the graph does not have an Euler circuit. Dahil obvious naman po na dapat all vertices have even degree. Ngunit may odd degree. Those are the definition and examples on how to determine an Euler path and Euler circuits.
Hey everyone, I'm Regine Kayla Esvelo and I'm from Tri5. Do you have any idea what is graph and Euler circuit, or who is Leonhard Euler? So for today, I will be discussing about graphs and Euler circuit, and I will give you some information who is Leonhard Euler. Leonhard Euler was a Swiss mathematician who is thought to be one of the greatest and most productive mathematicians of all time. There is more than one formula named after Euler, and the one we have just looked at is sometimes called Euler's polyhedral formula. Euler's other formula is in the field of complex number. A graph is a set of points called vertices, and line segments or curves called edges that connects vertices. Vertex means a corner or a point or line smith. Edge is a line segment between faces. A circuit is a path that starts and ends at the same vertex. Take note, vertices are always clearly indicated with a dot. Edges that intersect with no particular vertex are considered to cross over each other without touching. In general, a graph includes vertices that are not joined to any edges, but all edges connect the same vertices. They are called multiple edges. If an edge begins and ends at the same vertex, it is called a loop. A graph is called connected if any vertex can be reached from any other vertex by tracing along edges. Euler circuit is a path that travels through every edge only once. The degree of two vertices must be odd and the rest are even. If the Euler path starts and ends at different vertices, the Euler circuit is a path that traces every edge exactly once. They start and end at the same vertices. Euler's formula and Euler's identity. Euler's formula is e to the ix is equal to cosine x plus I sin x. Euler's identity is e to the ir plus 1 equals to 0. Euler's identity is often considered to be the most beautiful equation in mathematics. Euler's formulae are either of two important mathematical theorems of Leonhard Euler. The first formula is topological invariance relating the number of faces, vertices, and edges of any polyhedron. It is written f plus v equals e plus 2, where f is the number of faces, v the number of vertices, and e the number of edges. Example: a cube. A cube have 6 faces, 8 vertices, and 12 edges. So 6 plus 8 minus 12 is equals to 2. The second formula used in trigonometry says e to the ix is equal to cosine x plus I sin x, where e is the number of natural logarithm and I is the square root of negative 1. When x is equal to 2, the formula yields two elegant expressions relating to r, e, and I. Example: solve e to the ix for x is equal to r. We can write it as e to the ix is equal to cosine x plus sin x. Substitute x to the is equal to r, e to the ir is equal to cos r plus I sin r, and so forth. 1 cos r is equal to negative 1, sin r is equal to 0. So e to the ir equals negative 1 plus 0, or e to the ir plus 1 is equal to 0. Note that in this formula, the right-hand side is sometimes abbreviated as cis x, although the left-hand expression e to the ix is usually preferred over the cis notation. Thank you and God bless.
Hi everyone, I am Marian A. Saman and I am with
Mika Joy C. Saman. In this video, we are going to discuss what weighted graphs are.
First and foremost, what is weighted graph? Weighted graph is a graph in which edge associated with value which called weighted. The value can represent any quantity desired. Weighted graph is a graph that puts a weight to an edge. The weight might consider as the distance in the cities, the miles of travels, the time, and more. Now let's take this example to understand how the weighted graph works. Suppose a traveler would like to start in Chicago, visit the other 5 cities, these airlines do, and return to Chicago. Find 3 different routes that the traveler could follow, and find the total distance flown for each route. So, based on the problem, we will start to Chicago and then pass through the other 5 cities, which is airline flies to and return to Chicago. So, this is an example of a Hamiltonian circuit because we will start the same route or location, which is Chicago, and we have to pass through the 5 cities. So, the route that we need is a Hamiltonian circuit. So, before we proceed to the solving problem of the weighted graph, let us first elaborate the Hamiltonian circuit since we can use this on solving the problems of weighted graph. What is Hamiltonian circuit? Hamiltonian circuit is one of that passes through each point, exactly once but does not, in general, cover all edges. Actually, it covers only 2 of the 3 edges that intersect at each vertex. So we have here an example of Hamiltonian circuit. So it is a Hamiltonian circuit? The answer is yes, because it follows the definition of the Hamiltonian circuit, which emphasized that the path must visit its vertex exactly once and return to the starting point or vertex. So we started to Alameda and end at Alameda. But the question is why we didn't use the edge of the Fairmont to Burley and Burley to Dover. The reason is since our target or our main priority is to visit each vertex, therefore we are not supposed to cross all the edges as long as we can visit all the vertices. So now that the Hamiltonian circuit was already elaborated, let us go back to the solving problem of the weighted graph. So this is the table presenting the 5 cities with their corresponding number of miles. This is by the way in miles, so numbers in these rows and columns are in miles. So now this is our solution. Let's sketch a weighted graph first. So we will put a 9 dots or 9 vertices to represent the 6 cities. So from Chicago to New York, we will connect dots so its weight 713. So from Chicago to Washington DC, that is 597. So from Chicago to Philadelphia, that is 665. From Chicago to Atlanta, that is 585. From Chicago to Dallas, that is 803. From New York to Atlanta, that is 748. From New York to Dallas, that is 1,374. From Washington DC to Atlanta, that is 544. And from Washington to Dallas, that is 1,185. And from Atlanta to Philadelphia, that is 670. And from Philadelphia to Dallas, that is 1,299. So this is our weighted graph, so you just need to follow the table that being given in order for you to construct the weighted graph or sketch the weighted graph accurately. And now we will try to find the route, specifically Hamiltonian circuit, because that is being asked in the given problem. So let's try this route. We will start from Chicago and then to New York to Dallas and then to Philadelphia and then to Atlanta to Washington DC and then we go back to Chicago. So this is a Hamiltonian circuit. So this is our first route. Now let's find the total numbers of miles traveled by simply adding the corresponding weight in each edge. So we have here the Chicago to New York, that is 713, to New York to Dallas, that is 1,374. From Dallas to Philadelphia, that is 1,299. From Philadelphia to Atlanta, that is 670. From Atlanta to Washington DC, that is 544. And To Washington to Chicago, that is 597. So we will just add them the weight of corresponding edge to get the total number of miles traveled. So we get 5,197. So this means that we will traveling 500,197 miles if we will follow the first route. Let's take our second route. So we will start to Chicago, and then we go to Philadelphia, and then we go to Dallas, and then to Washington DC, and then to Atlanta, and then to New York, and then to Chicago. So this is our second route. So the same thing we did to first route, so we add the corresponding weights in every edge, so in order for you to get the total number of miles traveled. So in Chicago from Philadelphia, that is 665. From Philadelphia to Dallas, that is 1,299. So from Dallas to Washington DC, that is 1,185. From Washington DC to Atlanta, that is 544. From Atlanta to New York, that is 748. And then we go back to Chicago. From New York to Chicago, that is 714. Then we will add them so that we will be able to get the total number of miles traveled. So we get 5,154. So this is the total number of miles travels if we follow the second route. Now for our route, since we need to determine the third routes in this graph, so we could have this one. From Chicago, we will go to Washington DC, and then to Dallas, then to New York, and then to Atlanta, and then to Philadelphia, and then to Chicago. So similar procedure, we will be adding the corresponding weights in each edge to get the total numbers of miles being traveled, and that is 5,239. So take note that we are considering the Hamiltonian route in this graph because that is what being asked in the given problem. So we are asked to start in Chicago and then return to same location, which is Chicago, and then we have to pass through the 5 cities. That is why we're considering the Hamiltonian circuit. But the question is, which route is the shortest? The shortest route is the second route because second route has the shortest total numbers of miles traveled among the three. So that's it. That's how the weighted graphs work. So we hope that you learned and understood on how to sketch a weighted graph. So that's all. Thank you.
Salcedo Rose Annie, the Euclidean leader. We have here to learn more about the Euler's formula and also his life before he discovered the formula named after him. Now, I want to discuss to you the Euler's formula. Hope you like it. Leonhard Euler. He was born in Basel on 15th day of April 1707, also known as the greatest and most productive mathematician of all time. And there is more than one formula named after Euler. One of his formula is sometimes called Euler's polyhedral formula. His name pronounced Euler. His influencers: Johann Bernoulli. Bernoulli brothers are the friend of Euler's father. Johann Bernoulli was regarded as one of the best mathematicians in the world, so that Johann Bernoulli influenced young Euler in the years to come. Euler spent his Saturday afternoon to have lessons from Johann Bernoulli. Bernoulli quickly discovered that Euler had flair for math. Euler's formulae. Either of two important mathematical theorems of Leonhard Euler. The first formula is a topological invariance relating the number of faces, vertices, and edges of any polyhedron. It is written F plus V is equals E plus 2, where F is the number of faces, V the number of vertices, and E the number of edges. We have here the example. The cube, for example, has 6 faces, 8 vertices, and 12 edges. What would be the possible answer? Let's try this example. We have here the cube, and the formula F plus V is equals to E plus 2. We have here the value of F is 6 the faces of the cube. 8. The vertices of the cube is equals to E. The edges of the cube is equals to 12 plus 2. We're going to add 6 plus 8 is equals to 12 plus 2. 6 plus 8 is equals to 14. And 12 plus 2 is equals to 14.
Hi everyone, my name is Maria Cristina Waisalon and this is my partner
Mayrinel Aiza.
and we're going to report graph coloring.
Graph coloring. Graph coloring started in the mid-80s. Francis Guthrie tried to color the map of England so that it would be easy to distinguish the countries sharing a common border. Countries with the same border must have different color. A practical application of the graph coloring problem is in scheduling meetings or events. What is graph coloring? Graph coloring is a process of assigning color to the vertices of a group such that no two adjacent vertices of it are assigned the same color. Graph coloring is also called as vertex coloring. It ensures that there exists no edge in the graph whose end vertices are colored with the same color. Graph coloring is the procedure of assignment of colors to each vertex of a graph G such that no adjacent vertices get same color. The objective is to minimize the number of colors while coloring graph. The smallest number of colors required to color a graph G is called its chromatic number of that graph.
Coloring and chromatic number. A color for a graph is a coloring of the vertices in such a way that the vertices joined by an edges have different color. For example, in this graph, the end point of 1 and 2 vertices, one red and one blue. If you analyze any of the edges in this graph, you will see the two vertices are different color. It's possible that the coloring we're looking at is the least number color needed, and it's possible that it's not. But if we're told that this is in fact the minimum color, then we can determine its chromatic number by just counting the number of the colors. This diagram shows the minimum color of what's called Peterson graph. This is the chromatic number. If you said 3, you're correct because there are 3 colors required: blue, red, and green. If we attended to use 2 colors, it's possible to avoid having an edges with 2 same color in vertices. Graph coloring steps. Step number 1. Choose a vertex with high degree and color it. Use the same color to color as many vertex joined by an edges at the same color. Step number 2. Choose a new color and repeat what you did in step number 1 for vertex not already colored. Step number 3. Repeat step 1 until our vertices are colored. Now we're going to solve, but before that, we're going to put a degree in our vertices. Then we're going to proceed to step number 1. We're going to color the highest degree. I'm going to put red color in this degree. Bawal magkatabi ang same color, kaya kukulayan natin ang malayo sa kanya, yung hindi nakakonekta, na color red din. Isipin mo na lang ang color red vertex ay magjowa. Hindi sila magpinsan at hindi rin sila magkatabi, kaya parang LDR. Next step is step number 2. In this step, we're going to repeat what we did in step number 1. But we're going to use other color. I'm gonna put blue color in this vertex. Kaya nang sabi ko kanina, bawal magkatabi kaya lalagpasan natin ng isa. Tapos same din ang color nila, blue din. And then we will proceed in step number 3. Step number 3, repeat step 1 until our vertex are colored. Ulitin lang natin yung mga ginawa natin kanina, kukulayan lang natin yung mga wala pang color. Then the problem solved. Coloring of graph is used to solve practical problems such as scheduling problems in management science, allocating transmission frequency to a TV and radio station, study of cell phone traffic, coloring maps so that no two regions that share a boundary are the same color. Map coloring example. Use graph coloring to determine the latest number of colors that can be used to color the map of Southern Africa so that countries with common boundaries have different colors. Habang tayo ay gumagawa ng map coloring problem, sasabihin ko rin ang problem-solving strategy. Assign the level of each country. This will be your vertex. Number 2. Use edge to connect the vertex of countries that share borders. Use the procedure for coloring a graph. First, level degrees. Second, start coloring with highest degree vertex. And next, we're going to follow the graph coloring steps. Step number 1. Choose a vertex with high degrees and color it. Use the same color to color as many vertex joined by the edges of the same color. Step number 2. Choose a new color and repeat what you did in step number 1 for vertex not already colored. Step number 3. Repeat step 1 until all vertex are colored. The color of each region is the color of corresponding vertex. The result is a 4-color graph. It turns out that 4 colors are necessary for this map. All through other configuration are possible. The 4-color problem. Historically, mapmaker found that 4 colors sufficed for any map. Around 1850, mathematics started to consider whether this was true for all possible maps. In 1976, Kenneth Apple and Wong Gang Hacker used computer to prove the 4-color theorem. Because no human confirmed that result, some mathematicians do not consider it proven.
Hi everyone, I am Princess Kate Pasur Trianta, a BSED 1B. In this video, I am going to discuss about the modular arithmetic and I will give some example about this topic. The concept of modular arithmetic was developed of Carl Friedrich Gauss in his book This is Questiones Arithmeticae in 1801 when he was 24 years old. What is modular arithmetic? It is a system of arithmetic for integers where numbers wrap after they reach a certain value which is called modulus. In mathematics, it is sometimes called a clock arithmetic. So, let us talk about the congruence in modular arithmetic. It is the integers a and b are congruent modulo n, and write a congruent b mod n, if have the same remainder on division by n. How we can introduce modular arithmetic? The best way to introduce modular arithmetic is to think of the phase of a clock. The numbers go from 1 to 12, but when you get to 13 o'clock, it actually become 1 o'clock. Starting at noon, the hour hand points in order to the following: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0. This is the way in which we count in modulo 12. When we add 1 to 11, we arrive back at 0. The same is true in any other modulus or modular arithmetic system. In modulo 5, we count 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. We can also count backwards in modulo 5. Anytime we subtract 1 from 0, we get 4. So the integers from negative 12 to 0 when written in modulo 5 are 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0. The expression A congruent B mod M reads as A congruent to B modulo M. That means A and B have the same remainder when they are divided by M, where M is greater than 1. This is a simple example. A familiar use of modular arithmetic is in the 12-hour clock in which the day is divided into 12 hours periods. If the time is 7 o'clock now, then 8 hours later will be 3 o'clock. Usual addition, would suggest that the later time should be 7 plus 8 is equals to 15, but this is not the answer because clock time wrap around every 12 hours and 12-hour time. There is no 15 o'clock. Likewise, if the clock starts at 12 o'clock noon and 21 hours elapse, then the time will be 9 o'clock the next day. Since the hour number starts over after it reaches 12, this is arithmetic modulo 12. 12 is congruent not only to 12 itself, but also to 0, so that time called 12 o'clock could also be called 0 o'clock since 012 mod 12.
Hi everyone, I'm Jesseline Biblia Senior. I'm here to present to you what are those operations on modular arithmetic. Why do we study arithmetic modulo n? How is it important in our daily lives? You will be amazed that modular arithmetic help us in our daily living. Through modular arithmetic, we can easily know when is the next leap year and the days of our birthday without looking at the calendar. In computing the modulo operation, the remainder or signed remainder of a division after one number is divided by another. This is called the modulus of the operation. So basically, it is the possible remainder when one divides by the module. So modular arithmetic is a system of arithmetic for integers which considers the remainder. Let's define integers. Integers is a whole number that can be positive, negative, or zero, and not a fractional number or decimal. For example, 0, negative 1, negative 2, negative 3, negative 4, negative 5, and so on. And then 0, 1, 2, 3, 4, and 5, and so on. So those are the examples of integers. In this, I am going to show you how to solve the three operations of modulo n. So what are those? It is the addition, subtraction, and multiplication. For this addition modulo n, the formula is a plus b mod n. Example in number 1, 27 plus 34 mod 8. So 27 plus 34 is equals to 61 divided by 8 equals 7.625. So you need to get the whole number and eradicate the decimal places. So 7 times 8 equals 56. So 61 minus 56 equals 5. So 5 is the remainder of 27 plus 34 mod 8. And number 2, 39 plus 84 mod 7. You just need to add 39 plus 84 equals 123. Divided by 7, the result is 17.571. Just get the whole number, which is 17. 17 times 7 equals 119. So 123 minus 119 equals 4. Third example, 58 plus 73 mod 3. So the result is 131 and divided by 3. So 43 is the value. So get the whole number. 43 times 3 equals 129, and then 131 minus 129, the result is 2. So number 4, 89 plus 119 mod 8 equals 208 divided by 8. The result is 26. So 26 times 8 equals 208. 208 minus 208 equals 0. Remember that 0 belongs to integers. So, in multiplication. We just need to follow the previous procedure. So, the formula for multiplication modulo n is a times b mod n. Then, just follow the previous procedure, we get the correct answer. So, number 1, 18 times 27 mod 10 equals 486 divided by 10. The result is 48.6. Get the whole number. 48 times 10 equals 480. So 486 divided minus 480 equals 6. So next, number 2, 21 minus 32 mod 13 equals 672 mod 13 divided by 13 equals 51.69. So 51 times 13 equals 663. 672 minus 663 equals 9. So 9 is the remainder of 21 times 32 mod 13. Next, third example. 45 times 13 mod 15 equals 720 divided by 15. The result is 48. 48 times 15 equals 720. 720 minus 720 equals 0. So 0 is also an integer. Example number 4. 72 times 88 mod 13. The result is 6,336 divided by 13. 487.38. Eradicate the decimal places and get the value of whole number. So 487 times 13 equals 631. 6,331. So 6,336 minus 6,331 minus 5 equals 5. So 5 is the remainder of 72 times 88 mod 13. So in subtraction, sometimes confusing, but if you just follow the rules, you can solve it correctly. Example in number 1, 43 minus 18 mod 7 equals 25 and divided by 7 equals 3.5. Get the whole number. 3 times 7 equals 21. 25 minus 21 is equals to 4. So 4 is the remainder of 43 minus 18 mod 7. Here in this second example, in this case, our subtrahend is bigger than our minuend, so we will get the negative number, but take note that the negative answer is still an integers. So 27 minus 36 mod 6, the result is negative 9. So negative 9, since negative 9 is still an integer, we need to find the value of x so that negative 9 is congruent to x mod 6. So try to get the value of x by finding the value of x that are not that is less than 6. So example of which is 5, 4, 3, 2, 1. We just need to get the digit that is divisible by 6. So example is 3. So 3 is the symbol of x. So negative 9 plus 3 equals negative 12 over 6, and negative 12 over 6 equals negative 2. Third example, our formula is A minus B mod n. Number 3, 7 minus 9 mod 12 equals negative 2. So, negative 2 is congruent to x mod 12. Negative 2 minus x, by definition, negative 2 plus x over 12. So, let's find the value of x. So, yung hahanapin natin is yung digit na pwedeng i-divide, na pwedeng i-add sa 2 na magiging total siya ng 12. So, let's get that x is equivalent to 10. So, negative 2 plus 10 is equivalent to negative 12. So, negative 12 over 12, the result is negative 1. So, yun. Next, number 4, 50 minus 30 mod 13. So, 20 divided by 13 equals 1.5. Get the whole number. 1 times 13 equals 13. And the result is 13. So, 20 minus 13 equals 7. And take note that finding the value of x, this should be divisible by the value of x is divisible by the divisor.
Operation on modular arithmetic. Clock hour arithmetic. Modular arithmetic is sometimes known as clock arithmetic. Is one of the most familiar uses of modular arithmetic is in the 12-hour clock, which is the time period divided into 2 equal halves. Examples: Peter is online 10 hours ago, but now is already 8 a.m. What time Peter last online? Answer: 8 minus 10 is equals negative 2 plus 12 is equals to 10. If now is 3 a.m., Sharon went to the market 12 hours ago. What time she went to the market? Answer: 3 minus 12 is equals to negative 9 plus 12 is equals to 3. Now is 7 a.m. Our teachers instructed us that she will descend the link 23 hours after. So, what time you will receive the link? Answer: 7 plus 23 is equals to 30, minus 24 is equals to 6.
Good day, everyone. I am Rosal Riagas Velasco.
I'm Erica Otinyoso from
And I'm Francia Blanda Sardino, and we're from Euclidean Algorithm Tribe. Now we're going to present our topic about group theory.
So, shall we start?
In modern algebra is the study of groups, which are systems consisting of a set of elements and a binary operations that can be applied. This requires that the group be closed under the operation. The combination of any two elements produces another element of the group, that it obey the associative law, that it contain an identity element which combined with any other element leaves the latter unchanged, and that each element have an inverse which combines with an element to produce the identity element.
The axioms or basic rules for a group are closure, associativity, identity, inverses, and commutativity. Closure. If A and B are in a group, then A star B is also in the group. A set is said to close under a given binary operation star if for any two elements from the given set, the result from the binary operation is a member of the set. For example, the given set of real numbers. The set of real numbers is closed under addition, subtraction, and multiplication. Associativity. If A star B star C is equals to A star B star C, where A, B, C are elements of real numbers, then the binary operation star is associative. Associativity is defined as when more than two numbers are added or multiplied, the result remains the same, irrespective of how they are grouped. The following example shows that addition and multiplication of real number is associative.
Identity: there is an element A of the group such that for any element AO, the group A times E equals E times A equals A.
Identity: the natural element of a group is often called the identity element if the operation is writing in multiplicative notation, while it is called the zero element or null element if the operation is writing in additive notation. The symbols for the identity element is E or sometimes O, but you need to start seeing O as a symbol rather than a number. O is just the symbol for the identity, just in the same way E is.
Inverses: for any element A of the group, there is an element A minus 1 such that A times A, 1 equals E, and A minus 1 times A equals E. Inverses: the group contains inverses if we have an element of the group, there's another element of the group such that when we use the operator on both of them, we get E, the identity. In just the same way, for negatives, integers, the inverses are positives. Minus 5 plus 5 equals 0, so that inverses of minus 5 is 5. An inverses of an element is another element in the set that when combined on the right or the left through the operation, always gave the identity element as the result.
It is said to be commutative or abelian, a group in which the result of applying the group operation to two group elements does not depend on the other in which they are written. That is, the group operation is commutative.
That's it. Any mathematical system that obeys the four rules is a group. The study of systems that obey these four rules is the basis of this theory.
Subgroup is a group it contained with a bigger one, G. A subgroup of a group G is a subset of G that forms a group with the same law of composition. For example, the even numbers form a subgroup of the group of integers with group law of addition. A cyclic group is a group all of whose elements are power of particular element A. It is a group that is generated by a single element. It is a set of invertible elements with a single associative binary operation, and it contains an element G such that every other element of the group may be obtained by repeatedly applying the group operation to G or its inverse. Each element can be written as a power of G in additive notation. This element G is called a generator of the group.